Our next speaker is Professor Aggarwal from Columbia University. He's also a recipient of the Frontiers of Science Award, and today he will talk about universality for losange tiling local statistics. It's welcome.
So thanks very much for the introduction. It's a pleasure and honor to be here in Beijing. So I'll be talking about the behavior of random lozenge tiling. So let me start by explaining what a lozenge tiling is. So we'll start with the triangular lattice, which I'll denote by this boldface T. As you can see, all of its faces are equilateral triangles. It's shown, it's shown over here to the left. And we'll often use the term tile, lozenge, or dimer. These three words mean the same thing, so I'll often use them interchangeably. They're simply a pair of adjacent faces, so a pair of adjacent equilateral triangles. And you can quickly convince yourself that there are three possible orientations for these tiles. There's kind of this vertically pointing one and two horizontally pointing ones. And what we'll do is we'll consider tilings of subdomains of R of the triangular lattice using these three different types of lozenges. Okay, so as a basic example, we can take a hexagon of side length 2, which is shown over here, and depicted there is just a tiling of it, one example of a tiling of it. Okay, it will often be useful to also think of these these tilings, any tiling, as a step surface or as a height function. So as an example, we can take a look at this this hexagon over here to the left. It's a hexagon. It's a regular hexagon of side length about 15, and shown here as a tiling of it. And the tiles, the three types of tiles, are colored somewhat suggestively. So the vertical one, which is kind of saturating this corner where my cursor is colored in a medium shade of gold. One of the horizontal ones, kind of this one, is colored in a light shade of gold. So these are like here and here. And in a dark shade of gold is the other horizontal lozenge. So you have these three lozenges are colored in three different shades of gold. So now in addition to seeing a tiling, I hope you can also see what looks like a surface or a step surface. You can also think of this as kind of the corner of a room where the corner is kind of where my cursor is, and you're packing a bunch of boxes in that corner. Okay, and what you get after you pack in a bunch of boxes into that corner is a surface, and you can assign a height function to the surface that counts the number of boxes below any given point. Okay, so here's another example. This is an irregular hexagon of dimensions 3 by 4 by 5. Okay, so I've taken a tiling of it, an example of a tiling of it, and I've written down what the height is at each vertex in the domain. So here, for example, I'm claiming the height is 2, which hopefully makes sense because, as you can see, there are 2 boxes below this point. So, another way of thinking about this height function, which is entirely equivalent, is that I fix the height function to be something somewhere in the domain. So a common choice is to take your favorite point on the boundary and set the height function to be 0 there. So for example, you set it to be 0 at this vertex on the boundary. Then you have a tiling of it, and given any tile, if I know the height function at one vertex of the tile, I can extend it to the 3 other vertices. So for example, and the rule of doing that is shown over here. So for example, if I have a vertical tile, and I know the height function is h here, I can extend it to the other 3 vertices by setting it to be h plus 1, and h plus 1 here. And likewise, if I know any vertex in this picture, I can extend it to the other vertices. So in this way, given a tiling and given just the height function at one point in the tiling, I can extend it to the rest of the domain. So okay, these are all different ways of explaining, different but equivalent ways of explaining how to get a height function from a tiling. Okay, and the one point that is kind of non-canonical is I said I should define the height function to be something somewhere, right? So this is all up to an overall shift. So given a height function, there's kind of a given a tiling, there's a canonical height function that's defined up to an overall shift, which I get to choose. And this can be reversed as well. Whenever I have a height function on this domain, I can go backwards and get a tiling from it. So these are in bijection from each other, and I'll often think of them interchangeably. Okay. Okay, so now the boundary height function is simply the restriction. If I have any height function on my domain, it's simply the restriction of the height function to the boundary of the domain. So for example, here is a height function on the hexagon. It's defined everywhere. If I restricted the height function to the boundary of the domain, It's 0 on these two sides of the boundary. It's 3 on these two sides of the boundary. It's linearly increasing here. Okay, and it's a quick exercise. It's not so hard to show that if I have any domain, there might be many, many tilings of it, which all give rise to different height functions. But all of these height functions share the same boundary height function. So every domain is basically gives rise to a boundary height function, which uniquely determines it, basically. So boundary height functions and domains can basically be thought of as in correspondence with each other again.
Can your height functions have local extrema?
Well, yeah, these are going to be monotone height functions. Yeah, that's right. As you can imagine, by this cube, by packing a bunch of boxes into a corner of a room, these will have, they'll be monotone this way. Okay, so this is all deterministic. I have not put any randomness in the game yet, so now I'm going to do this next. So we're going to consider tilings of very large domains. Given a very large domain, there may be many tilings of it, and I want to pick one, put all of these tilings in a hat and pick one uniformly at random. Okay. So equivalently, you can think of this as the dimer model in large subdomains of the hexagonal lattice. Okay, and the basic question we'll be interested in is how do uniformly random tilings of very large domains look? And maybe the best, just to get a feeling for it, one can start with an example. So here is a simulation of a tiling of a fairly large hexagon, maybe of cell length around between 30 and 50, something like this. And as you can see, a uniform and random tiling of it is picked. And as you can see, it has some non-trivial structure. So there's this inscribed circle, outside of which the tiling doesn't look random at all. It looks actually completely deterministic. Near the corners, the tiling is just saturated. The tiling is just saturated by one type of tile, basically. That forms a kind of shingle work pattern. And inside the circle, the tiling looks much more random, right? It actually looks kind of random. So often these regions where the tiling has a shingle work pattern is totally deterministic. We call these frozen regions. And the region where the tiling looks much more rough and random, I'm being somewhat vague here, is called the liquid region. And the boundary that separates the liquid from the frozen is commonly referred to as an Arctic boundary. Okay. So what are some features of random tiling? So the observation that goes back to Castellan over 60 years ago is that the behavior of random tilings is very much dependent on the shape of the domain in which you're tiling. Okay. So here I've shown 5 different examples. So one is a hexagon, one is an octagon, one is a 12gon that kind of looks like a rotated S, one is a triangle with kind of jagged sides, and one is a parallelogram. And as you can see, these have different behaviors. This hexagon is more or less the same as from the previous slide, except it's colored slightly differently. This octagon, it also has, if you look closely enough, it might be too small, but if you look closely enough near the corners, you'll see that the tiling has these kind of frozen regions again. And you also have this Arctic boundary separating these frozen regions from a liquid region. But this Arctic boundary is no longer a circle, it's now a different curve that's in fact a cardioid. Qualitatively, a somewhat similar phenomenon holds with this S, although the liquid region has a more complicated, the boundary of the liquid region is still more complicated. And this triangle, you actually don't see a frozen region at all. It looks totally disordered all the way to the boundary. And in this parallelogram, the whole thing looks frozen. And the parallelogram is maybe the simplest to explain. There's just one tiling of it, and that's the tiling. Okay. So that's one feature of these models, is that it depends strongly on the shape of the domain. The other feature, which has kind of been solidified over the past 30 years, is that the local geometry of these tilings is very homogeneous. And I already kind of hinted at this notion in the previous slide. If I fix my domain, say the hexagon or this kind of rotated S, if I poke at different parts of the domain and ask myself how the tiling looks, it can be very different. For example, if I look kind of near the corner, as I already mentioned, I only see blue tiles near this corner. Whereas if I look kind of deep inside this circle, this inscribed circle, I'll see all 3 different types of tiles, and they'll kind of be randomly interspersed, right? So this is just a way of saying that these random tilings kind of are very homogeneous locally. So these 2 features of having like a very strong dependence on the domain and being inhomogeneous locally, these are features that are common in highly correlated statistical mechanical models, for example, in other random surfaces or random crystals. And the goal is to understand these phenomena quantitatively. Okay, so this talk will be featured on, this talk will be focused on local features of tiling. So the game that I'm going to play is I'm going to take a domain, I'm going to make it big, I'm going to scale it if you like to be very big, and I'm going to look at different parts of the domain, and I'll look at local neighborhoods of different parts of the domain, and I'll ask myself, how does the tiling look in different local neighborhoods? So there are various choices at points I can pick. One is kind of the bulk, the interesting part. The bulk of the interesting part. So I can like take this this inscribed circle. I can look at a point strictly in the interior, and I can look and say a 10 by 10 window of that. I might, or okay, in this case it might be something like a 4 by 10 window or something like, yeah, maybe about a 4 by 10 window, and I'll get a random tiling now on this 4 by 10 window that looks something like this. So I can ask myself, what does it look like near there? Another natural point to zoom in, so I probably don't want to zoom in near the corners. I'm not going to get something too exciting there. But what I can also do is I can zoom in where around the Arctic boundaries, so where the liquid region starts to become frozen. So over here, you're kind of being saturated by all green tiles, but just before that, you have a few red and orange tiles before it becomes fully green. So at this kind of phase transition, where liquid becomes frozen. That's often called the edge of the facet, where the green part is sometimes thought of as a facet. Okay, yet another place that's natural to zoom in is this Arctic boundary. The circle meets the boundary at a few places, 6 places, these 6 tangency locations. You can try to zoom in near these tangency locations, and something interesting or different that happens there is on either side you have saturation by tiles, but by 2 different tiles. So near this tangency location, you can see like if I kind of go far to the left, I'll be saturated by orange or I guess yellow-orange tiles. And here I'll be saturated by red tiles, and then you have some green tiles separating them. So these are different places where you can zoom into this model and see different behaviors, different limiting statistics. So the goal is to understand these limiting statistics and how they depend on the domain. So I mean, this kind of proceeds in 2 steps you can think of. You can pick your favorite domain and compute the limiting statistics on that specific domain. That's maybe a first step that will give you some sense of what the answer should be. And then I kind of want to understand how it depends on the domain. So what I want to show is that whatever limiting statistics I just computed for my specific domain appear universally. So if I take any domain, however complicated, I'll have the same kind of universal limits that will appear if I start probing places like this. Okay. So I'll try to give you an outline of what kinds of results you can prove, and then I'll start stating results more precisely. So as I mentioned, my goal is to understand these different limiting local statistics and how they depend on the domain. And there are 3 different regimes, the 3 that I pointed to in my previous slide. You can look at the bulk of the liquid region, which corresponds to looking in the disordered region, the liquid region, picking a point in the interior and seeing what the tiling looks like locally around any point. And I'm listing, in each of these 3 regimes, I'm listing 2 results. The first result is among the first results that was proven on a specific domain, kind of the first step, this computation step on a specific domain. And the second step is kind of the universality statement that says, in what generality is it now known that these statistics appear? Okay, so I'll go through some of these later on in the talk. I just want to give maybe the experts an indication of what's now known, and this will hopefully also give a guide as to what the rest of the talk will be about. So in the bulk of the liquid region, again, kind of in the interior of the liquid region, you'll get what's often called an ergodic translation invariant Gibbs measure. I'll say what that is in a few slides. And that was originally proven in the torus in the work of Cohn Canyon Prop in 2000, and about 5 years ago, which was the paper for which I guess this talk is about. It was shown that this fact the same measure appears on general domains. Okay, so then you can look at near the edge of the facet. So the special domain chosen there was the hexagon, so the one from the previous slide, and it was shown that you get something called the area line ensemble, and the independent works of Johansen and Bike, Creature-Bauer, McLaughlin, and Miller. And in recent work with Jiayang Huang, we show that this appears on a wide and likely generic class of polygons. If almost any polygon will have the same kind of property. And near a tangency location, you get something called the Gaussian unitary ensemble corners process. This was originally shown in the specific domains of the hexagon or certain families of skew plane partitions in the independent works of Johansen Nordenstam and Okonkwo-Reshettikin. And in work with Vivian Gordon, we basically showed that this holds around any tangency point on a general domain. Okay, and I should say that there are many results between these two bullet points for all of these three examples, and I'll try to survey them towards the end of the talk. Okay, so this was maybe I was saying a bunch of words here. I'll try to now state some results more explicitly. I'll try to get through the first part, and I have slides on the second part, but it's not clear whether I'll get there, and I probably won't get to the third part. So yeah, okay. So let me start by trying to explain these words mentioned in the bulk of the liquid region more precisely. But before I get to local statistics, my game was totally local, right? I'm taking a point and I'm zooming in around there. I want to first give just one slide telling you what the global behavior, the full behavior of the model looks like. This is a somewhat easier and less, this is a less fine-grained problem because I'm allowed to, when I look on a broad scale, I'm allowed to have a lot of error. Okay. So there are two reasons for doing this. First, it's obviously very natural, and second, the objects that appear, which are quite non-trivial, that appear in the answer for the global limit, will play a role in the local limit. So it will actually be useful for me to describe the global limit first. Okay, so so let's set this up. So as I mentioned before, I'm going to take a random tiling of a massive domain. I also mentioned that tilings can be associated with height functions, right? So what's going to happen is that this height function on a large scale will concentrate, it will be close, and will converge to a deterministic height function. So this is some version of the law of large numbers or a limit shape phenomenon that the surface associated with the tiling will converge to a deterministic surface that you can describe. Okay, so let me set this up a little bit more precisely. So we'll let mathfrak R. So this fractor font will always denote the continuum side, and the Roman font will denote the discrete or tiling side. Okay, so we'll let this mathfrak R be a simply connected macroscopic domain with piecewise smooth boundary. These conditions can be relaxed, but let me not do that. These are kind of general enough. And okay, so this is some continuum domain. You could think of it like a trapezoid over here. And we'll consider some large integer n, which you should think of as kind of the diameter of the domain you're going to tile, and you're going to let R, or R sub n, be some simply connected tileable domain that is a kind of, it's approximately an n-fold scale of this mathfrak R. Okay, so you're kind of blowing up this domain up to form some tileable domain, which I'm denoting by this Roman R. As I mentioned before, once it's tileable, I can assign a height function to any tiling of it. And the boundary height function, the restriction of the height function to the boundary doesn't depend on the tiling, right? It only depends on the domain. So that means associated with this R is a boundary height function that I'm denoting by h or h sub n. And it's a map from the boundary of this domain R to the integers. And we're going to assume that it has a limit, okay? So which is natural. I mean, just some limiting behavior as n tends to infinity. We're going to assume this. So I mean, the precise statement is that if I scale down this boundary height function by n, then it will converge to a boundary height function on my continuum domain that I'm denoting by this mathfrak R. Okay, and we'll let h or h sub n be a height function associated with a uniformly random tiling of this tileable domain R. So we're picking a random tiling of this domain here. We're going to let h be the height function associated with it. And the question is, what does this h behave like as n tends to infinity? Okay, and the theorem that goes back to Konkani and Proper around 25 years ago is that there's a deterministic limit shape, a non-random limit shape h that lives kind of on the continuum side, such that if I scale down this Roman height function, the tiling height function by a factor of n, it will converge to this calligraphic, this non-random limit shape calligraphic h as n tends to infinity. Okay, so this is and you can say more. You can actually say what this non-random limit shape is. It's going to be the minimizer of a certain variational problem. Okay, so in particular, it's going to be the minimizer f, which is taken over all functions, Lipschitz functions, on this domain, this frac domain R, with the correct boundary data, with this correct boundary condition, that minimizes a certain action, which is like which we'll denote by it's going to be sigma, where sigma is some function of the gradient of f, okay? So you can think of this as some kind of, so as a vague analogy, you can think of soap bubbles on a wireframe, right? So soap bubbles on a wireframe, I have some wireframe and I create a soap bubble on it. It will form a minimal surface, right? Which is also, I mean, minimal surfaces can be described as minimizers of a variation principle where the sigma is going to be the area functional, okay? And the wireframe is kind of the analog of this H. It's telling what the boundary condition is. So, okay, so in this case, a somewhat similar phenomenon is happening. This tiling limit shape is going to converge to the minimizer of a variation problem. Now for tilings, this sigma is explicit. It's actually given by a sum of Lobachevsky functions. Okay, I have not written it down. It's a bit complicated, but it is totally explicit. And the difference between what happens in the minimal surface, say, problem and tilings is that this sigma is not strictly convex. So in particular, this H will satisfy a degenerate elliptic equation, and one will often have to deal with these issues when analyzing these limit shapes. Okay. So I mean, the moral of the slide is that this high function H associated with the random tiling of a big domain converges to a non-random limit that solves a variation problem that is kind of complicated. It's non-trivial. Okay, now let me go back to my original goal of understanding the local behavior of these models. So let me kind of just set up the problem, or set up at least a baby case of the problem that will give you some sense of what we're talking about. Okay, so again, we'll take some domain R of the triangular lattice, and we'll fix a vertex V inside of R, okay? And the basic question is, what is the probability of seeing a given pattern of tiles around V? So as a basic example, imagine that R is a regular hexagon, okay? And let's say that V is its center, okay? And one example of a pattern is just seeing a specific tile. So I can ask the question of what is the probability of the center face of R being covered by a vertical lozenge? It can be covered by any of the three lozenges, right? So what's the probability that it's vertical? Well, I mean, so symmetry should tell you what the answer is. I mean, the hexagon has is invariant under rotation by 2 pi over 3, right? So that means that any tile should have equal probability of being covered by of covering the center face. So that would immediately tell you the answer is a third. Okay. Now I can ask a more complicated. I can study a more complicated pattern, which is what is the probability that the center face and the face directly to the right of the center face. So I have this hexagon. Maybe the center face is here, and the face right next to it is the face directly to the right of it is here. And the question is, what is the probability that both of these are covered by vertical tiles? Okay. So the probability that this one is covered by a vertical tile is 1/3. And you can imagine that, okay, this is not exactly at the center, but it should morally be the same. So this one should also be a third. So if those two events were independent, the answer would be 1/9. But in fact, it's 1/9 minus 3 over 4 pi squared. Okay, so you get a somewhat non-trivial answer there. Okay, so my goal is to understand questions of this nature, right? What is the probability of seeing various patterns near a given vertex? And I'll consider a somewhat more general setup so that we can consider much more general problems than this specific one mentioned over here, which is that, again, we have some big domain, we have a vertex V in it, and we'll consider some order 1 neighborhood of V. And maybe it will be a bit more convenient to, okay, so yeah, I consider some order 1 neighborhood of V, and I have some tiling of my big domain that will restrict to some tiling of that order 1 neighborhood. So as an example, you have this big hexagon, that's my domain R. I have some point V inside, which is maybe where my cursor is. I take some order 1 neighborhood of it, which is kind of this green little square, which I've zoomed in to this. So I have some random tiling of this sort of order 1 neighborhood. And the question is, what is the probability of seeing a given local pattern in this neighborhood? It's a bit more convenient to take a kind of inverse limit of this process. So we'll first let the size of this domain R go to infinity. So this hexagon, we're just going to make this very, very big. We'll take a random tiling of it. And then instead of making this domain of order 1, we're going to let it tend to infinity, but much, much, much more slowly than how the original domain is tending to infinity. So first you let the hexagon or whatever domain you're considering go to infinity, and then you let this green domain go to infinity. So you're kind of looking at whatever this vertex can kind of see locally. So any kind of finite distance is covered in this domain. Okay, so then after I do that, I'll get a random tiling, my random tiling of my big domain, will restrict to this random tiling of my growing neighborhood. That growing neighborhood will kind of exhaust the triangular lattice in the limit, and what I'll get is some random tiling of the triangular lattice. So this will now, so I'll get some random tiling of that triangular lattice, and this will contain any pattern that I'm after, right? Well, in particular, it will contain the pattern I drew over there, but it will contain all local probabilities will be contained in that kind of that growing neighborhood. So as I mentioned, it's kind of inverse limit of this problem. Okay, so the bulk statistics question is what is the law of this random tiling of this neighborhood as I make this neighborhood very large. Okay, as I said, this will answer a much more general question than this one. It will tell me the probability of seeing any pattern, any bounded pattern of tiles around my vertex B. Okay, so the broad prediction is that any candidate mu. So okay, so the question is, what is the law of this tiling on this sort of full plane after taking this limit? Okay, so the broad prediction is that any candidate mu for this limit should have three properties. The first is translation invariance, which simply means that if I apply translation to it, it does not change. It's invariant under shifts of the lattice. The second is extremality, which means that I cannot break it up into two non-trivial components. And the third is the Gibbs property. So this is a fancy name for something that's by far the most obvious of these three, which is the following. So it's basically a statement of saying that this tiling is uniformly random. But remember, I've taken my green domain, this kind of green square, off to infinity. So I can't consider a uniformly random tiling of the full plane, right? There are infinitely many of them. I can't pick one uniformly random. So instead what you do is you restrict to finite domains and you impose that you're uniform on those. So what you do is I have some infinite or finite tiling, say this one here, but you can imagine these tiles going off to infinity in all directions. So this is maybe just a little piece of the full tiling. I cut out some subdomain of it, like the black one shown here. Okay? And I condition on everything outside of this black region. I condition all this stuff. Okay? And this again might kind of be an infinite conditioning. I'm conditioning on everything here. Okay? And so the question is, what's the law of the remainder? What's the law of the stuff inside of this black region? So if I kind of imagine I can erase what's inside the black region and then resample it. And the answer is that it has to be uniform. But now if I look at this black region, there are only finitely many tilings of it. So I can pick one uniformly random, and this so-called Gibbs property is a statement that the conditional law inside this black region is uniform. Okay. This is kind of natural, and this is fairly natural. And it's not very hard to see that any finite tiling will satisfy this property. So this is already true kind of in the finite back on this slide. If I already take a finite but very large domain, this Gibbs property is exactly satisfied. So if I take a limit, it will also continue to be satisfied. So the Gibbs property is kind of the easiest to check among these three. The extremality and the translation invariance are much more subtle. In fact, they can be false for certain models, for certain very natural models, in fact. Certain variants, certain 6 vertex models, these are false for. So this is a point of caution. Although this is a broad prediction, this prediction has some defects. So it's not always the case. Okay, for depending on which model you pick. Okay, so the first bit here is just a repetition of the previous slide. Okay, so I've said that any candidate should satisfy these properties, conjecturally or as a prediction. Okay, running with this prediction, if you kind of grant it to be maybe true, you can ask, okay, what do things like this look like? What do measures satisfying these three properties look like? So it's a theorem due to the thesis of Sheffield around 20 years ago that given a proportion of tiles, so given a ST, given a pair of real numbers S and T, where you should think of S as the proportion of vertical tiles and T as the proportion of this kind of horizontal tile. So 1 minus S minus T would be the proportion of this kind of tile. So given this proportion of tiles, there's a unique translation invariant extremal Gibbs measure on tilings of the full plane. So there is kind of a unique measure that fits the bill for all these three conditions if I fix the proportion of tiles. Okay? And we'll often say that this measure has slope ST, and that's because the height function associated with, if I take the expectation of that height function, it'll be linear, but literally will have slope ST. Okay. Okay, so I've given you a kind of existence statement and a uniqueness. I mean, I've given you a prediction for what this thing must look like, and kind of an existence and uniqueness statement that's somewhat abstract. It doesn't tell you anything about this measure. This measure can actually be described explicitly as follows. So there's an explicit and fairly, in my opinion, very, very beautiful description of what this measure is. One description of this measure was due to the work of Kohn-Kenyon Prop and also by Kenyon around the turn of the millennium. I'll describe a slightly different looking, although equivalent description of this measure due to Okunkov and Rashatikin. So to explain it, let me take any tiling, and it's a quick exercise to convince yourself that any tiling that has a positive proportion of all tiles is determined by the locations of the vertical tiles. So if I just know where the vertical tiles are here, that fixes the rest of the tiling. Okay, this is not hard to see. I mean, already here, if a vertical tile here and a vertical tile here, you can quickly see that this is forced to be horizontal in this direction, right? Okay, so I'll let X of M be denote the set of centers of all of the vertical tiles in my tiling. So it's the set of these black dots. Okay, so if I want to describe the tiling, all I have to do is describe the set Xm. Okay, and there's a formula that describes the set X of M. Okay, and it's the following. So I'll let St be any numbers between 0 and 1, and I'll describe the set X of M sampled under this translation invariant, like this mu of St, this translation invariant extremal gives measure of self St. So I'm going to describe this Xm and therefore the full tiling under this probability by a formula basically. And this formula says that, let's say I'm going to ask, what is the probability that some set of points, x1, y1, x2, y2, all the way up to xm, ym, are in the set xm? If I can do this for any set of points and for any m, I've nailed down the set xm. These are the so-called correlation functions of x of m. This is given by an m by m determinant whose entries are explicit. I don't want to necessarily, I wrote down the formula just to convince you that it's explicit, though I don't really want to go into the details of this formula. I mean, this is a determinant, this is an m by m determinant. The entries are these k. This k is given by an integral from some point xc bar to xc in the complex plane, where xc is explicit in terms of s and t. Okay, so you can compute everything you want with this. So this kind of structure, whenever you have something like this, is often called the determinant point process, when these correlation functions can be expressed as a determinant of some big matrix, as a determinant of actually a minor of some big matrix. And this is very useful for determining local probabilities. In particular, if I want to compute that picture that I had drawn over there, I'm basically computing the probability that I have two vertical lozenges right next to each other. Okay, well that's just this probability with m equals 2. x1, y1 is say 0, 0, and x2, y2 is 1, 0. Okay, so I can just plug it into this formula now. On the right side, I get a 2 by 2 determinant, and the answer will be s squared minus sine squared pi of s over pi squared. Okay, and if you plug in s is equal to a third, you'll get exactly the answer that I advertised before of 1/9 minus 3 over 4 pi squared. Okay, so that's how you get that answer from the previous slide. Okay, and for those of you who are aficionados of random matrix theory, you might quickly recognize this as the analog of the sign kernel for eigenvalues of a random Hermitian matrix. Okay, so this is a discrete version of that. Okay, so now I will describe the theorem, the bulk statistics theorem. Okay, so let me just remind you of the setup, which is, at least most of it, is going to be similar to the global, the limit shape. So that's part of the reason why I mentioned that earlier on the talk. So, well, again, so the fractor notation is going to be on the continuum side, and the Roman notation is going to be on the tiling side. So we'll let R be a simply connected set with piecewise smooth boundary. Again, you can think of a trapezoid or any kind of complicated domain you like. Again, these conditions of simply connected and piecewise smooth can be relaxed, but let me not try to optimize this any further. We'll again fix a large integer R, which you should think of as the diameter of the tileable domain, and we'll let R or R of n be the n-fold, be some tileable domain that's approximately an n-fold scale of this frac R. We'll let m, again, I'll often decorate it by an n, I'll sometimes decorate it by an n, denote a uniformly random lozenge tiling of this domain. So here is one realization of mn. Okay, and so now this is all the same as before. And now what I want to do is I want to look locally around a vertex. So I need to fix a vertex and then look locally around it. Okay, so I'm going to first fix the vertex on the continuum side, which I'll call this frac V. Okay, so that's living at some point here, and I'm going to let st denote the gradient of the height function around V. So this height function, the gradient of the limit shape. So this is the limit shape from the previous slide. that's given as the minimizer of the somewhat complicated variational principle. Okay, so this is the H. That's kind of the global law, the law of large numbers for my height function. Okay, I'm going to compute its gradient at V, which I'll denote by ST. So you should think of ST as kind of the local slope around this point V. Okay, and we're going to assume that ST and 1 minus S minus T are all non-zero. What that basically means is that you have a non-trivial proportion of each kind of tile. Okay, you need this because otherwise you're in the frozen region, which you don't want to be, right? I want to be in the liquid region. I want to see all types of tiles and see that randomness. So I want all of these numbers to be non-zero. Okay? So yeah, these strict inequalities imply that B is in the interior of the liquid region. Okay, now that's on this continuum side. On the discrete side, I'm simply going to let V be a point whose that's a scale of the corresponding scale of this math product V. Okay, so it's basically a scale by a factor of n. Okay. Okay, now the statement is, as n tends to infinity, the local statistics of this random tiling around my point V are given by this translation invariant ergodic Gibbs measure mu of st. So again, if I take a domain, like a neighborhood, an order 1 neighborhood of V, I first let n tend to infinity, and then I let this neighborhood tend to infinity. I'll get some tiling of the full plane, and that tiling, some random tiling of that full plane, and that random tiling is exactly this mu s of t. Okay, so in this form, this was predicted by Cohn-Kenyon prop in 2000, although they attributed a prediction of this nature to the earlier physics work of Castellan in the early 1960s. And you can think of this as a universality statement because what you're doing is you're computing kind of infinitely many probabilities, right? You're computing the probabilities of any kind of local pattern of which there are infinitely many, and you're saying that this full family of probabilities only depends on 2 numbers, which is the gradient of my limit shape at this point, h of v. So you kind of have infinitely many local probabilities only depend on 2 parameters in the large scale limit. Okay. Okay, so I probably won't have time to go through the facet edge, so let me skip that. Okay, so I'll quickly mention some previous methods and results. So previous methods were basically mainly based on algebraic frameworks that picked a specific domain and computed these local probabilities exactly. Okay, so one mechanism for doing that was observed in works of Castellan and Kenyon and the physics and math literature respectively, which on a high level basically says that random tilings are determinants of point processes. So maybe in words, what this is saying is that any kind of probability that I'm interested in, any kind of probability of any pattern, is expressible as the determinant of a certain matrix. Okay, now the determinant of a matrix is only as good as the matrix itself, right? If the matrix is a disaster, then this is maybe not so useful. And the matrix is called, it has a name, it's called the inverse Castellan matrix. Now an issue is that in many cases, in certain examples, you can compute this inverse Castellan matrix, and you can understand what it's doing in the large scale limit. But in general, this is actually quite difficult. It remains a difficulty. It was and remains a difficulty to understand what this matrix is doing on very big and very general domains. Okay, so on special domains, one knows how to. In certain special domains, one knows how to take the limit of this inverse Castellan matrix. So a few examples: the original work of Cohn-Kenyon prop on the torus that manages to compute the limit of the inverse of this matrix in that case. There are a series of works on the hexagon between 2007 and 2009. Various trapezoids or infinite versions of trapezoids one can compute these limits for. So that was done between 2012 and 2017. And for hexagons that kind of have a cut, you can imagine a hexagon with a dent on both the top and the bottom. That's also known how to take the limit of that inverse Castellan matrix. There are also alternative approaches that don't at least directly rely on the inverse Castellan theory, based on representation theory. The key words are Schur processes or Gelfand-Settler patterns. This was pioneered in the work of Okunkov and Reshetkin, who was analyzing these limiting local probabilities for skew plane partitions. And over the subsequent decade or two, this technique had also been fruitful for analyzing these statistics on various other domains. There are also a few probabilistic domains. There are also a few probabilistic methods that kind of combine some of these to obtain slightly more general domains, such as the work of Vadim Gorin, who analyzed domains covered by trapezoids that can kind of be Yeah, basically, I mean, I won't define what this exactly means, but you can, yeah, I mean, there is some covering of your domain by trapezoids. And then lastly, I also showed that these bulk statistics are kind of stable under perturbation. So if I just like remove one tile from the boundary, I make some microscopic dent that doesn't change the local statistics. Okay, so but broadly speaking, these techniques, I guess maybe one limitation of them is that they basically handled one domain or one class of domains at a time. So maybe an advantage of the present results is that they were able to prove the results for arbitrary domains simultaneously. And the proofs qualitatively, so I mentioned that there were 3 regimes, even though I only had time to discuss one of them. It's kind of the bulk of the liquid region. There was the facet edge, where the rough region becomes, the random region becomes frozen, the liquid region becomes frozen in these tangency locations. And there's always on a very high level, and maybe impressionistic level, there's some kind of unifying theme to the proofs in all of these 3 regimes, which is that they have 3 components. The first is an analytic step, which broadly speaking is you prove an a priori estimate on the tiling of a general domain. So you take your general domain, which could be fairly nasty, and you prove some bounds. You don't really go for the exact statistics, but you just prove some estimate for the tiling on this general domain. So an example that you might want to keep in mind is a concentration estimate. So you have your height function. You show that it concentrates around some profile with a very, very small error. So the analysis is kind of minimizing that error in a sense. Okay, and I won't go into the details yet about what kinds of errors you want. Okay, the second step is an algebraic step, which is you locate a specific family of solvable domains for which the limiting statistics can be proven. And I already gave a ton of examples on the previous slide. And the third is a kind of probabilistic step. So you use this rough analytic bound, to locally couple the tiling on your general and maybe nasty domain to one on a solvable domain. So as a basic example you might have in mind is you take your complicated domain, I look locally around a vertex, and in some neighborhood of that vertex, I'm going to sandwich it between 2 solvable domains. Okay, and if those 2 solvable domains are close enough, that actually says that all 3 domains, the 2 things you're sandwiching in between and your nasty one, are all the same. But that just means that, I mean, you're kind of done at that stage, right? Because I know what the solvable thing is doing, and the one that I a priori don't know, the general one, is sandwiched between them. So I'm in business. Okay, so this is kind of a very impressionistic or general or vague explanation of the type of strategy. I should mention that the implementation of the strategy for the 3 different regimes is quite different. So since I kind of made a chart here. So this is kind of the regime, like kind of the bulk of the liquid region, the edge, and the tangency location. This is the statistic that you find. I already mentioned this measure μst. I didn't get to talk much about these. The estimate is different. The form of the estimate is different. So in the latter 2, you kind of use a concentration estimate with some error that you need. And for the bulk, you need what's often called the local law. So this is reminiscent of the local law that appears in random matrix theory through the works of Erdős and Yau. And the solvable domain also kind of, you have to pick a different one depending on which regime you're probing. Okay, so for the bulk region, the thing that was the focus of this talk, you look at kind of non-intersecting random walks, which you can kind of imagine as an infinite trapezoid, where you let the height of the trapezoid go into infinity in a certain sense. Okay, so let me just conclude with all of this. So as I said before, random Wilson challenges are very sensitive to their boundary conditions, and local behaviors differ depending on where you probe the domain. I mainly focused on the bulk of the liquid region where you see an ergodic translation invariant Gibbs measure. Previous results showed that these statistics occur on special domains, and the recent results showed universality phenomena, indicating that these limiting statistics appear universally on fairly general domains. And the proofs are based on a combination of algebra, analysis, and probability, where the analysis is being used to obtain a coarse estimate on your general domain. So at this stage, you kind of have to face the fact that you're dealing with a nasty domain, but you're requiring less, just a bound. The algebraic step is where you require more. You kind of require getting the refined limiting asymptotic statistics, but now in a specific domain. And the probabilistic step is where you kind of couple them together. Okay? So with that, I'll thank you for your attention.
Questions?
Thank you for the great talk. My first question is about does your method or the result holds for more general diamond models such as domino tilings?
Okay, so the method, at least for domino tellings, I would be optimistic. Although I mean, one would have to work. But I would be optimistic that the general strategy should work there. I have not thought carefully about the other ones, so that is maybe not something I'd be able to answer reliably on.
So for domino tilings, your method will extend rather easily?
Sorry?
So
It's not. It would not be a completely trivial extension, but I would imagine that kind of each lemma in the or each statement in the original paper should have a counterpart for the domino telling. Proving those counterparts would require some effort, I would imagine. But I would be optimistic that this is kind of doable.
I see.
Yeah.
So my second question, in your main result, you mentioned you work for a tileable domain. But if we think reversely, we first pick an arbitrary domain, whether how can we know it's a limit of a tileable domain?
You're asking how can you know if... Oh, on the continuum side. So
yeah. On the continuum side, we pick an arbitrary domain. So how can we say it's a limit of a tileable domain and goes?
Okay, so the tileability of the domain. Okay, this is somewhat ironic. So the tileability of this. So you're saying given R, how do you know it's tileable?
Yeah.
Okay, so the tileability of R, ironically enough, is not determined by R, but rather by H. Okay, so whenever you have a height function H, so I mean the R actually doesn't matter very much. You can often pick. There's often some discretization of R that gives rise to a tileable domain. The tileability of that domain is kind of determined by H. So whenever you can write down a height function on like this H on your domain, and if it has a Lipschitz extension, if this H has a Lipschitz extension to the interior of R, and you can discretize that, then you have a tiling.
I see.
Yeah.
Thank you.
Hey, well, thanks for the great talk. Two questions. So first, this uniqueness of the mu-st measure, that indicates that there is some kind of decay of correlations, right?
Yeah.
So do you have some, sort of intuitive way to explain why this correlations decay, first of all? And secondly, is there some kind of rate of decay that's known, or is it exponential, or?
Yeah. Okay, so let me answer both of these questions. So what you can do, you can play the game that's often played in percolation. Let me before I say that, you take two independent tilings of a given domain and you can overlay them. Okay, so what happens when you do that is that each vertex, each face, is covered by a dimer, right? And so this might be dimer in one family, and then this might be a dimer, like this might be a dimer in another family. So you can keep on doing that, and what you'll get is a circuit, basically, by just chaining together these tiles in these two tiles. So you'll get a family of circuits or loops. And what basically happens is that decay of correlations is more or less equivalent to the notion that these circuits have crossing estimates, much like what you see in percolation. Okay. So that's not. So that would, if that were true, that would imply a polynomial decay of correlations. That's believed to be true in the liquid region. Okay, that's not a theorem though. So, but the reason you expect to have some kind of correlation decay is the fact that these circuits satisfy phenomena similar to circuits in percolation. And in fact, there's a that is somewhat formalizable. If that were true, if the circuits obtained by laying two dimers on each other did satisfy those kinds of estimates, it would be a corollary that you would have decay of correlations of the same nature. Proving that those estimates is non-trivial due to boundary conditions, basically. And the theorem that I mentioned here does imply correlation decay, but a much worse one than algebraic. It would be some logs, yeah, like 1 over log n or something like that. Yeah, I would not brag about that. Correct. In the liquid region. So if I take 2 points in the liquid region, it's conjectured to be polynomial. Yeah.
So a couple of questions regarding what is within reach from what you have discussed today. So you've discussed the bulk and the edge asymptotics. Probably when we speak about the cusp, about the Pearcey, it should be similar.
In fact, it's not only should be, it's a theorem of Fan Yang, who's sitting in the few rows in front of you, and Jiayang Huang and Lingfu Zheng. So they proved that statement for the cusp as well. Yeah.
Okay.
And what you get is a limiting statistic that's often called the Pearcey process.
Mm-hmm. And next, when we switch from the uniform case to say that, for example, talk by Alexei Borodin, when we speak, say, about two periodic weights,
Yeah.
and for example, the liquid region, do you expect something within reach, or is it?
Yeah, this I would not. Yeah, I don't see. So there, I mean, so the statements should be correct in the argument, but I mean, now I would not know how to prove some of them, or at least offhand. So the family, actually, the issue, ironically enough, is in the solvable part. So I mean, the second step is incomplete there in a sense. So the work of Alexei might make one, or Alexei and Thomas might make one fairly optimistic that maybe this can be improved in the context of doubly periodic domino tellings. And if that were the case, if you could kind of find out, if you can prove counterparts of the statement in that context, you would be able to run through the argument. But since that's not done yet, I would not have an immediate answer for you. Yeah.
Okay, thanks.
Yeah.
Okay, do we have more questions?
Thank you for your excellent talk. And I have a small question. Can we extend this method to, for example, a stochastic six vertex model to show the convergence to the Gibbs measure?
Okay, so for the stochastic six vertex model, this is actually done before this result. It's an easier problem, in fact. The fact that the model is stochastic is Markovian simplifies things because what you're doing in that model is you're kind of not pinning down the full boundary. You're only pinning down part of it and then evolving it, right? Like you have some quadrant and you have your arrows coming in, and you're not pinning down what happens here. This is kind of free under the stochastic six vertex model. So so the fact that you have that you converge to the local Gibbs measure is a theorem there that was proven by myself in around 2018. Yeah. It's not directly related to the scheme, I should say. It's a different argument. Yeah.
More questions? You don't know.
Sorry, I'm a complete outsider, but I just want to ask, can you give a very brief feel for how you'd be able to prove what's involved in showing translation invariance of the Gibbs measure?
Well, yeah. So this is a challenge, and it's somehow not always true. So the proof does not proceed by showing these three properties. Instead, it proceeds by finding some domain on which I know that this measure is, where I see this measure, and then coupling it to it. So I don't actually prove these three properties independently. Instead, you couple it to a domain that I already know everything about. In particular, I know these three properties, but maybe I don't really care that much. Yeah.
Thanks.
Yeah.
Questions? If no more questions, let's thank all speakers in the afternoon.